I'm Anil Kumar, and in this video, we're going to explore complex numbers in polar form. We'll consider to find product of complex numbers, their quotient. We'll have examples for product and quotient of complex numbers. We'll prove the de Moivre's theorem. We'll write a complex number in polar form in a plus bi form. We'll find powers of complex numbers and also the roots of complex numbers. So that is all we are going to do in this particular video. So let me just remind you that in the complex plane, we actually have along the x-axis, we call this actually real axis, right? And the vertical axis is called the imaginary axis. Now any point in this plane, in this complex plane, could be represented by numbers in complex form or also in polar form, right? For example, if I have a number here, z equals to x plus iy, it could be written as equal to r times cos theta plus I sine theta. So that is how they could be written in the complex form, correct? Where the angle theta is always with the positive real axis and theta has to be between 0 to 360 degrees, or you can say 0 to 2 pi. And r, the amplitude, is greater than, always greater than equal to 0, is always positive, right? So these are the constraints. Transformation between these two, as you know, is x equals to r cos theta and y equals to r sine theta. So that's the background. From here, let's begin and find product of complex numbers and their quotient. So in the very first exercise, we will see how to find product in general of complex numbers written in polar form, right? So all this is about polar form. So if we have two complex numbers in polar form written as z1 equals to r1 cos theta 1 plus I sine theta 1, and z2 is r2 times cos theta 2 plus I sine theta 2, then we'll find out what is z1 times z2. That is the product, correct? So when you multiply them, we get r1 times cos theta 1 plus I sine theta 1 times r2 times cos theta 2 plus I sine theta 2, right? So r1 times r2 is product of these two, so we can write this as r1 r2. Distributive property, we get cos theta 1 times cos theta 2, then we get plus I cos theta 1 sine theta 2, then we get plus, we'll write here, plus I sine theta 1 cos theta 2. I square is negative, sine theta 1 sine theta 2, correct? So that gives us product of r1 and r2 times. Now if you combine the terms, which are cos theta 1, this is cos theta 2, and sine theta 1 sine theta 2, what do you get? You get cos theta 1 plus theta 2, right? Compound angle formula. And here, these two terms, if you combine, you get I sine theta 1 plus theta 2, right? So you get I times sine of theta 1 plus of theta 2, right? Combination of these angles. So that is what happens when you find their product, right? Now, so basically their magnitudes get multiplied and the arguments get added. So that is the net result. The product gives us, in short, magnitudes get multiplied and arguments get added. Now you can actually pause the video and also find the quotient. So if you do quotient of these two, that is Z1 over Z2, what do you expect? We'll expect R1 over R2, and these get subtracted. So we get cos of theta 1 minus theta 2 plus I sine theta 1 minus theta 2, right? So you'll find that in complex numbers written in polar form, multiplication is very straightforward and simple. Let's move on and really see how we get that. So now we'll do the quotient form. So if I divide one by the other, I get Z1 over Z2 equals to R1 over R2. And the numerator, we have cos of theta 1 plus I sine theta 1 over, denominator is cos theta 2 plus I sine theta 2. Now what we can do is that we can multiply by the conjugates. We can rationalize kind of the denominator, right? So if I multiply both numerator and denominator by cos theta 2 minus I sine theta 2, then what do I get? Right, so let's do this. You can actually pause the video, simplify from here onwards and see if you get the result which is expected, correct? So now what we get here is that we have R1, the ratio of these two, cos theta 1 times cos theta 2 minus I cos theta 1 sine theta 2. Then we'll multiply by this term, which is plus I sine theta 1 cos theta 2, and I square is negative, it becomes positive here. We get sine theta 1 sine theta 2, correct? Theta 1 sine theta 2. Okay. Divided by a square minus b square, which is cos square theta 2 minus I square sine square theta 2, right? So R1 over R2 is cos theta 1 cos theta 2, as we did before. We'll combine these terms, which is clearly equal to difference of these angles, arguments, right? So we have cos of theta 1 minus theta 2. And as far as the sine components are concerned, we can take minus common. And if I take minus common, I get sine theta 1 minus sine theta 2 inside, right? So we get minus I common. And we get here, let me write this term first, sine theta 1 cos theta 2 time plus, because we have taken minus common, this becomes, okay, let's keep it positive. So then in that case we get I cos theta 1 sine theta 2, and then we get R1 over R2 times difference theta 1 minus theta 2. Well, denominator I didn't write here. Let me write denominator. That becomes a square. Sorry for that. So here we have cos square theta 2 plus sine square theta 2, which is 1. I square is negative 1, correct? So when you do that, you get negative as 1 here in the denominator, and the numerator you get plus I sine theta 1 minus theta 2, correct? So when you do quotient of these numbers, then we get ratio of amplitudes, and difference of arguments. Is it okay? Now let's move on, and here is a practice question for you to find product and quotient of complex numbers in polar form. If z1 equals to 2 times cos 20 degrees plus I sine 20 degrees, and w equals to 3 times cos 100 degrees plus I sine 100 degrees, let me make this just z. In that case, let us find their product. That is, we need to find what is zw, right, their product. So from what we have learned, the product is product of R1 and R2, which is 2 times 3. And the arguments get added up. So what we get here is cos of 20 plus 100 degrees plus I sine 20 degrees plus 100 degrees. So that gives us 6 times cos of 120 degrees plus I sine of 120 degrees, correct? So that becomes the product of these two. Now if I have to find quotient, so let's say z over w, for example, then in that case R1 gets divided by R2, which is 2 over 3. And what we get here is cos difference of these arguments, which is 20 degrees minus 100 degrees, plus I times sine 20 degrees minus 100 degrees. So that gives you 2 over 3 cos of minus 80 degrees plus I sine of minus 80 degrees. Now you should remember that the value of r should always be positive, r should always be greater than or equal to 0, and the argument theta should be between 0 to 360 degrees. Okay, so if you get negative angles, you have to rewrite that as an equivalent angle, correct? So basically what you've got here is an angle of minus 80. Minus 80 means we are talking about this angle. We have to write this as a principal angle, right? So we go write this as 2 over 3, 360 minus 80 degrees, correct? So that becomes the angle, which is cos of 360 degrees minus 80 degrees plus I sine of 360 degrees minus 80 degrees, correct? So this is a very critical step. You should not really miss on this, correct? So now we get our final answer, which is 2 over 3 times cos of 280 degrees plus I sine of 280 degrees. Correct? So that is how you find product and quotient of complex numbers in polar form. Now let's try to prove De Moivre's theorem. We have already learned if I multiply two complex numbers in polar form, what do I get? That is to say, we know that if z1 is equals to r1 cos theta 1 plus I sine theta 1 and z2 equals to r2 times cos theta 2 plus I sine theta 2. In that case, the product of these two complex numbers is product of R1 and R2 times cos of sum of the arguments theta 1 plus theta 2 plus I sine theta 1 plus theta 2, correct? Now, in our case, when we do power, right, so let's say we want to find z square, for example. Is it okay? So what are we doing here? In that case, we are writing z's are cos theta plus I sine theta. So if I have to square it, in that case I can apply this formula directly. Basically, R1 is equals to R2 is equals to R, and theta 1 is equals to theta 2 equals to theta. So that becomes 2 theta, right? And this becomes R square. So applying this formula directly, what do we get here? We get R square times cos of 2 theta plus I sine 2 theta, right? So basically sum of angles, right? Sum of angles. Now if I do z cube, in that case what happens? So let's continue with this pattern. R times cos of theta plus I sine of theta whole cube. So cube you could also consider as z square times z, correct? And then apply this formula. That means we are doing product of these two. So you could do like this also. In that case, what do you get? You get r cube, and the angle is theta plus 2 theta, correct? So we get cos of theta plus 2 theta plus I sine theta plus 2 theta, right? Which is r cube cos of 3 theta plus I sine 3 theta. So we could actually generalize this result and write z to the power of n as equals to r to the power of n times cos of n theta plus I sine of n theta. Perfect. So that is what is the De Morgan's theorem. So I hope it is absolutely clear. It is extension to our product rule. You could also prove it by induction. Okay, let's move on. Take some examples. So here is one example. We need to write 3 times cos 20 degrees plus I sine 20 degrees to the power of 3 in the form of a plus bi, right? So we have 3 times cos of 20 degrees plus I sine 20 degrees to the power of 3. Now it becomes 3 cube. We'll apply the formulas. We could write this as 3 cube, and inside it becomes cos of 3 times 20 degrees plus I sine 3 times 20 degrees, correct? So that gives you 3 cubes 27 cos of 60 degrees plus I sine 60 degrees. Perfect. You can use calculator, or you can have you can use this special triangle 30, 60, 90. So where for 60 degrees we have the sides 1 to square root 3. Using these values, we can write it as 27 cos of 60 degrees is half plus I sine of 60 degrees square root 3 over 2. Correct? So we could write this in this particular form. So now it is in a plus bi form. If I open the bracket, I get 27 over 2 plus I 27 cube root 3 over 2, right? So that is the complex form a plus bi, where you know the magnitude will be 27. So I hope that is straightforward. So let's move on, take few more examples. Now let us try to find the fifth power of a complex number minus 1 plus I square root 3 in the form of a plus bi. Now whenever we are talking about complex numbers powers, it should remind you of De Moivre's theorem, right? So we'll apply De Moivre's theorem. Now we are given minus 1 plus I square root of 3 to the power of 5. Well, if we say that z is equal to minus 1 plus I square root of 3, in that case, what is the magnitude? Magnitude of this complex number is square root of minus 1 square plus square root 3 square, right? Which is square root of 1 plus 3, which is 2, right? So the magnitude is 2. So we can write this complex number z as equal to 2 times minus 1 over 2 plus I square root 3 over 2, right? So that is how we can represent it. Now, in the complex plane, now this number will be represented in, that's the cosine value negative, sine value is positive. So somewhere in quadrant 2, right? So that is the point which will be represented on the complex plane. So this is real and this is imaginary. Correct? So that is how we are going to represent it. And that's the angle theta we are talking about. So for minus half, what is going to be the angle? Let's look into our special triangle. 30, 60, 90, right? So for 60 degrees, we know this is 1, 2 square root 3. So we know this angle theta should be equal to, acute angle is 60. This is 60 degrees, correct? So the angle theta will be 180 degrees minus 60 degrees. Perfect. And therefore, we can write z as equal to 2 times cos of 120 degrees. Let me write this as 120 degrees, right? Cos of 120 degrees plus I sine of 120 degrees, correct? So that is what z is. Now, we have to find the fifth power of z. That means we have to do 2 times cos of 120 degrees plus I sine 120 degrees to the power of 5. Now we can apply De Moivre's theorem and get the result, which is 2 to the power of 5 times cos of 5 times 120 degrees, right? Plus I sine of 5 times 120 degrees, correct? Which is 32, and cos of 5 times 120, 5 times 2 is 10, 600 degrees. Plus I sine 600 degrees, right? Now, you should remember that whenever we are working in complex plane, theta is between 0 to 360 degrees, correct? So we'll write its equivalent angle, so which will be 600 minus 360, that gives us 240 degrees, correct? So we can write this as 32 cos of 240 degrees plus I sine 240 degrees, right? So that is how we can find the fifth power of the given function, right? So I hope that's absolutely clear. It's a very important theorem to use, and it can help us to find the powers and also the roots, right? So in the next example, we'll see how to find root of a complex number in polar form. So now, the question here is, we need to find complex cube root of minus 1 plus I square root 3. You can pause the video, try this out, and then look into my suggestions. Now this is the last exercise of this video. Let us recall all our steps. We need to find the cube root of the complex number minus 1 plus I square root 3. So let me write down the complex number z as minus 1 plus I square root of 3. So first step is find the magnitude of this number. So we get the magnitude of z as equals to square root of minus 1 square plus square of square root 3 square root, and that gives you square root of 1 plus 3, which is 4, and square root of 4 is 2. So we could write this complex number z as equal to 2 times within bracket minus 1 over 2 plus I square root 3 over 2, correct? Now this is in quadrant 2, correct? So this complex number is in quadrant 2, where the angle is 180 minus 60 degrees, right? So this angle is 180 minus 60 degrees, just as we did in our previous example. So I've taken the same numbers actually. Okay, so we could write this complex number as 2 times cos of 120 degrees plus I sine of 120 degrees, correct? So that is the first step. You need to write your complex number in the form of in the polar form, correct? So that is what it is. Now what are we interested in finding? We actually want to find the cube root, right? So let us say that the cube root is ZC is the cube root of this number. Is it okay? Then using the De Moivre's theorem, we can actually say that the cube root is equals to cube root of 2, right? Cube root of 2 times cos of the angle here, which is 120 divided by 3, plus, because this number 2 pi is the time when it is repeated, right? So it is 360 degrees n over 3 plus I sine of 120 degrees divided by 3 plus 360 degrees n divided by 3. So that is how you're going to get the cube root. Now the power is 1 over 3, right? Therefore it comes in the denominator as shown here. Now that gives you cube root of 2 times cos of, now when you divide 120 by 3, you get 40 plus 120, let me write n for time being. So cube root means we are expecting 3 roots, right? So we can put n as 0, 1 and 2 to get our 3 roots. Plus I sine 40 degrees plus 120 n. Now the 3 cube roots will be for n equals to 0. So that is cube root of 2. You will find that the magnitude is same. Magnitude is cube root of 2. And if I substitute 0 here, I get cos of 40 degrees plus I sine of 40 degrees, correct? The second root, I mean, we start z1. Substituting 1 here, we get cube root of 2 cos of 40 plus 120 degrees plus I sine 40 plus 120 degrees, great, which is cube root of 2 cos of 160 degrees plus I sine 160 degrees. Perfect. And the third cube root will be magnitude same, cube root of 2. We'll replace n by, so what we are doing here, for different roots, we are replacing n by 0, 1 and 2. So cube roots will be 3. So if I replace it by 2, we get cos of 40 plus 2 times, means 240, plus I sine 40 plus 240 degrees, which is cube root of 2 cos of 280 degrees plus I sine 280 degrees. So we get 3 different cube roots for the given function. Now what you notice here is very important, which is their magnitudes are same. So let me just plot and show you what do we get here. Their magnitudes are same, which is, that is their magnitude. Is it okay? So that means we have found 3 cube roots which are kind of points in this direction. Correct? Angle of 40 degrees, quadrant 1. Angle of 160 degrees, slightly less than 180. And 280 degrees, slightly more than 270, right? So all these 3 points will actually fall on a circle, since this magnitude is same, right? So they fall on a circle. And they are spaced equally apart. Correct? So this angle here is 40 degrees. And then between each, we have 120 degrees. Do you see that? The angle between them is 120 degrees. So if we are finding the cube root, in that case, we'll divide 360 by 3 and get the 3 roots. And the magnitude will be cube root of the magnitude of the complex number itself. So that's a very important concept. It gives you overall picture how easily we can find roots of this, right? So as an exercise, what you can do is we can extend this to, let's say, 5th root, right? So if I have to find the 5th root of minus 1 plus I 5th root, then what do you expect? Well, the answer should be, we are looking for the same magnitude, that is 5th root of 2, right? And the angles will be, instead of divided by 3, equally spaced, and they'll be divided by 360 divided by 5. Is it okay? So in that case, it'll be 360 divided by 5. That will be the spacing, 72 degrees, right? And the very first angle is going to be 120 divided by 5. So 120 divided by 5 equals to 24 degrees. So what we expect, let me show it here. So in that case, we expect a pentagon inside a circle whose angles are spaced. So our value is 5th root of 2, right? And the angle will be 20. What did we get? The angle will be, for this particular function, 120 divided by 5. 120 divided by 5, which is 24 degrees, right? So this will be 24 degrees. And each will be plus 72 apart. 96 kind of, right? So we'll have the other point here. So we have 5 different roots and they'll be 72 degrees apart, correct? So we get a pentagon inscribed in a circle with radius of 5th root of 2. Is that clear? Right. So we get a pentagon inscribed in circle with radius equals to 5th root of 2. Do you get the idea, right? So that is how you can easily work with complex numbers in polar forms. It's very easy to find their powers and their roots. So I hope you understand and appreciate it. If you like and subscribe my videos, it'd be great. Feel free to write your comments and all the best.